Kamahara Foundry, established in the 1950s, specializes in manufacturing large steel castings, especially for ships and defense vessels. As one of the few Japanese foundries capable of producing castings up to 40 tons, the company takes pride in contributing to national security and preserving traditional craftsmanship. The corrugated steel production process is a continuous cold rolling process that converts flat steel coils into sheets with trapezoidal or corrugated folds. This method ensures high precision and efficiency in mass production. The process begins with coil preparation. A large steel coil is loaded into an unwinder. Workers feed the end of the steel strip into the forming line. The tension is carefully controlled to avoid distortion or misalignment during the feeding process. The second stage is shaping, in which the flat steel strip passes through a series of rolling stations. Each station consists of upper and lower rollers, which gradually bend the steel into the desired shape. The gradual shaping on multiple rollers ensures uniform and precise corrugation while preventing cracks or material fatigue. The number and design of the rollers determines the final shape of the corrugation, which is usually trapezoidal or sinusoidal. When the sheet reaches the required length, it moves to the cutting section. Here, an electromechanical guillotine is precisely synchronized with the moving sheet. The guillotine quickly drops and cuts the sheet to a preset length without stopping the production line. This ensures continuous, high-speed operation. After cutting, the finished corrugated sheets are automatically stacked and prepared for packaging or shipping. Throughout the entire process, sensors and controllers monitor size, alignment, and speed to maintain consistent product quality. This efficient production method ensures strong, lightweight, and uniform corrugated sheets for use in roofing, fencing, and construction applications. Goratu is a famous company with lathes, milling machines, a multi-function machining center. DEEG's metalworking suite leads the industry with precision, strength, and flexibility. At its core is the Gemini series of CNC horizontal lathes engineered for large-scale applications. These heavy-duty flatbed machines support workpieces up to 24 meters long and over 150 tons in weight, ideal for power generation shafts, railway components, and oil and gas equipment. The GTI series boasts rigid structures, high-torque headstocks up to 106,000 Newton-meters, advanced ergonomics, and customizable multi-axis options including C and Y axes, grinding spindles, and quick-change tooling to reduce setups and maximize throughput. Complementing these are lagoon milling machines, robust vertical mills celebrated for precision and versatility. In the Goratu factory tour, a GHTM model demonstrates tight tolerance milling, drilling, and boring, all controlled seamlessly via CNC. D-Tougher still is DEEG's GHTM multi-process machining center. This multitasking powerhouse integrates turning, milling, drilling, reaming, and even grinding into a single setup. The result: less downtime, superior part accuracy, and cost-effective production. Quick change accessories and smart features like thermal compensation and predictive maintenance apps align perfectly with Industry 4.0 best practices. Together, these platforms illustrate DEG's commitment to customization, eco-design, and operator-centric innovation. Whether handling massive cylindrical shafts or complex multifunctional parts, the Geminis lathes, Lagun mills, and GHTM centers deliver unmatched rigidity, precision, and efficiency, making DEG the go-to partner for modern heavy-duty machining solutions. The production of the XDF engine began with designing key gas components, followed by testing the gas admission valve for reliable performance. Engineers then measured valve lift, hydraulic response, and control signals to ensure optimal functionality. The pilot injection valve and gas valve unit were also tested and refined. Full-scale manufacturing of the 6X62DF engine took place at Doosan's facility. Through careful development and rigorous validation, the world's first low-speed, low-pressure 6X62DF engine was successfully realized, making it ideal for powering large LNG carriers. The large crankshaft grinding process begins by securing the crankshaft a line grinding wheel. Advance wheel slowly, rotate shaft evenly, remove minimal material. The process of making bamboo chairs begins with the selection and preparation of the bamboo slats. The bamboo slats are heated over an open fire, an important step that serves both functional and aesthetic purposes. The heat treatment process removes any remaining organic material in the bamboo, which significantly reduces the risk of insect infestation and prevents termite damage. This heat treatment increases the durability and longevity of the final product. Furthermore, the high temperature changes the natural color of the bamboo, creating unique wood grain patterns and a polished surface, which greatly improves the aesthetics of the chair. After heating, the bamboo slats are cut to the desired length and drilled to create precise holes, known as mortises. These holes are strategically placed to allow the various bamboo pieces to be assembled, forming the frame of the chair. The main structure consists of vertical and horizontal members that interlock to form the frame and legs, creating a sturdy and balanced base for the chair. Some of the bamboo was softened through exposure to higher temperatures and gently bent to form the curved backrest. Once shaped, the curved bamboo is inserted into the previously drilled mortise holes on the back legs. The fit is tight and secure, ensuring a stable connection. The frame is further reinforced by a combination of joints, wooden dowels, and screws. These connections are important to maintain the overall integrity of the chair during use. The seat surface is secured with screws that tighten the seat surface to the chair legs. Each screw is carefully aligned and spaced to create a comfortable and secure seating surface. The craftsman ensures that all components are securely fastened. Next, the mortise holes are refined and bamboo dowels, crafted from solid bamboo, are driven into these holes to connect the different parts of the chair. These dowels strengthen the joints and provide a natural, seamless look. The use of bamboo dowels adds strength and traditional craftsmanship to the design. Throughout the process, the craftsman pays close attention to symmetry, fit, and finish. The result is a durable, elegant bamboo chair that combines function, strength, and aesthetic appeal, crafted almost entirely by hand using sustainable materials. Submerged arc welding is used to weld the longitudinal and circumferential seams of cylindrical pressure vessels. An automated system moves the welding head along the joint, while a layer of granular flux covers the arc. The flux shields the weld from contamination and stabilizes the arc, ensuring deep penetration and high-quality welds. Sparks and slag are formed as the molten metal solidifies. The aluminothermic welding process for joining railway rails is a highly precise and controlled procedure. It begins with the preparation of a straight and perpendicular welding gap between the two rail ends. This gap is usually created using either a disc cutter or a flame torch, guided by a cutting gauge to ensure accurate width and angle. After cutting, the rail ends are aligned properly. The outer edges of the rail foot and the running surfaces must match exactly, and a specific crown is introduced to compensate for vertical shrinkage during cooling.
Up to under the rail head. Then the reverse foot, and finally the rail head must be cut. Pulling the rails can also be used no foreign body to be within the metal sleeve.
Next, the preheating torch is selected based on the gap size and pressure settings, as defined in the welding code. The torch is mounted on a burner saddle, and its height and position are adjusted precisely using a setting gauge to ensure the flame covers the entire cross-section of both rail ends. The flame must have equal length and proper height on both sides. The rails are preheated until they reach a uniform temperature between 900 to 1000 degrees Celsius, indicated by a yellow-red color.
Flame develops a rattling noise. Then close the combustion with the aid of removing of one mold half. Here, it is viewable how the preheating flame equably heats the complete cross-section area. When preheating using compressed air and gasoline, then the setting of a stable blue preheating flame is very eminent. Finishing the preheating, the torch is to be removed. For this, the crucible is
Once the correct temperature is achieved, the molds are installed. Depending on the type of rails, vignole, grooved, or crane, 2-part or 3-part molds are used. These molds are positioned tightly around the gap and sealed using luting sand or luting paste to prevent molten steel from leaking. Cardboards are inserted around the mold head to form a controlled void that will be filled by molten steel during the reaction. For worn or mismatched rails, additional cardboards are used to close any gaps under the rail foot or head.
After another waiting time after pouring, the mold head including the slag is put off. The running surface is to be cleaned of all residues. A hydraulic trimmer is used to cut the excess metal from the weld. The cutting height over the running surface is limited due to the
crucible is then prepared. For long-life crucibles, it is essential to dry them internally to at least 100 degrees Celsius to prevent moisture-related defects. The thermit portion is poured into the crucible, and an igniter is used to initiate the aluminothermic reaction. This exothermic reaction produces molten steel, which flows into the mold once the tapping thimble melts. The slag, being lighter, follows and is collected in slag pans.
An incorrect preheating time, as well as specific portion grades. All these facts will be imparted during the welder's training. All welding material on the running surface and on running
After
frame
pouring,
will be
the
graded
crucible
off.
and slag
The
pans are
shrinkage done
removed
is
and placed on a
finished
non-flammable
before the
surface.
ambient temperature is reached.
The molds remain in place for a specified cooling
Therefore,
period.
a small
Once
oversize
solidified,
can remain
the
after
mold head
rough
and
grinding.
excess material are removed using a
Pieces
hydraulic
reassembled
trimmer.
and tightened
Final grinding
fasteners.
is done to restore the
mold
rail
could now be
profile to its
passed
original
by a running
specification,
wheel.
including the running surface, radius, and flanks. Dimensional
Only when the
accuracy is
weld
checked
completely
using a
cold
straight
can
edge
you
and
remove
feeler
the mold
gauges.
residues and knock
Once
off
all
the
checks are
razors at the
complete
rail
and the
front.
weld is fully cooled, the joint is marked,
Surface,
concluding the
the head radius,
aluminothermic rail
and
welding
running flank
process.
is to be-
Wind turbine blade cleaning is carried out by a professional team. The rope access team is performing wind turbine blade cleaning on the 1.65 megawatts NEG Micon wind turbine at the Vestas site in Udumalpit. Certified technicians use a rope access method to safely descend from the nacelle and position themselves on the blade surface. Each technician is equipped with a safety rope and cleaning tools. First, they anchor the rope to the top of the turbine and slowly lower themselves to reach the blade. Once in position, they begin cleaning using a high-pressure water gun and environmentally safe cleaning agents. The technicians carefully remove dirt, dust, bird droppings, and other contaminants that affect the aerodynamic performance of the blade. This process is done meticulously to ensure that the blade surface is not damaged. Cleaning is performed on all three blades by rotating the rotor as needed. The team works together to complete the job efficiently. Once completed, they will slowly rappel down the tower body. After the cleaning job is completed, the ropes will be retrieved and the area secured. This rope access method allows for a quick, cost-effective, and thorough cleaning with minimal downtime. The 2,000-ton open die forging press is used to shape large sheets of metal under extreme pressure. First, the heated billet is placed on a press table controlled by a control unit. The press then applies a controlled downward force to compress and stretch the material. The operator controls the clamp to rotate and reposition the billet between punches to achieve the desired shape. This multi-directional forging process enhances the internal structure and strength of the metal. Finally, the forging is allowed to cool before further processing, such as trimming, machining, or heat treating. The rolling process at Lucchini RS begins with an integrated production system that eliminates intermediate warehousing. Preheated billets are moved directly into a massive 23-meter diameter rotating furnace, capable of processing 40 tons per hour. Once the billets reach the required temperature, they are transferred to two hydraulic presses rated at 9,000 and 5,000 tons, which perform the initial forming of the wheels under intense pressure. After pressing, the semi-formed wheels are fed into a highly advanced rolling machine equipped with 13 computer-controlled axes. This precision system shapes the wheels to exact specifications, accommodating diameters up to 1,450 millimeters. The rolling machine ensures consistent geometry and quality, contributing to a production rate of up to one wheel every 58 seconds. Subsequently, the wheels are conveyed to the new railway wheel heat treatment line. This automated line performs controlled heating and cooling cycles to optimize mechanical properties such as hardness, strength, and durability. Each step is continuously monitored and adjusted to meet stringent performance standards required for railway applications. The seamless flow from forging to rolling and final heat treatment maximizes efficiency and ensures high-quality wheel production in a fully integrated process. The ring rolling process begins by loading the pre-forged ring onto the D53 CNC ring rolling machine. Using Siemens PLC control, the machine precisely positions the ring. Radial rolling is initiated as the main roll compresses the ring against the mandrel, reducing wall thickness while increasing the diameter. Simultaneously, axial rolling reduces the ring's height, with two vertical rolls applying downward pressure. The synchronized radial and axial deformation ensures uniform shape and material flow. Throughout the process, the CNC system monitors and adjusts parameters to maintain accuracy. The final ring, with diameters ranging from 350 to 8,000 millimeters and heights from 60 to 800 millimeters, is then removed. The milling process begins with dynamic planar milling on a DMC 1450 volts machining center. Using the high-feed 6 cutter with a 63 millimeters diameter head and insert type T350M, the tool is mounted on holder. The workpiece material is. Cutting parameters are set to a cutting speed of 350 meters per minute, spindle speed of 1,770 revolutions per minute, feed per tooth 1.1 millimeters, feed rate 11,600 millimeters per minute, depth of cut 1.0 millimeters, and width of engagement 30%. Next, plunge milling is performed with the same tool. However, the cutting speed is reduced to 237 meters per minute, spindle speed to 1,200 revolutions per minute, and feed per tooth to 0.08 millimeters. The feed rate is 600 millimeters per minute, axial depth of cut 10 millimeters, and AE 50 millimeters. Then, the process shifts to high-feed helical milling, still with the 63 millimeters head and same insert. Cutting speed is 250 meters per minute, spindle speed 1,263 revolutions per minute, feed per tooth 1.0 millimeters, feed rate 7,500 millimeters per minute, AP 1.0 millimeters, and AE 80%. For more complex sections, a 52 millimeters cutter and steady line damped holder are used for plunge milling. Parameters are VC 220 meters per minute, N 1,350 revolutions per minute, FZ 0.09 millimeters, VF 600 millimeters per minute, ASO 6.24 millimeters, AE 27 millimeters. In helical milling with the same setup, VC is increased to 250 meters per minute, N to 1,530 revolutions per minute, and VF to 6,000 millimeters per minute, with AP 0.8 millimeters, AE 70%. In 5-axis simultaneous milling, both the high-feed 6 and Jabro Solid 2 end mill are used. The Jabro tool operates at VC 210 meters per minute, N 5,570 revolutions per minute, FZ 0.17 millimeters, VF 3,788 millimeters per minute, AP 45 millimeters, and AE 1 millimeter. Finally, 4-axis simultaneous turn milling is done using the Turbo 12 cutter with VC 276 meters per minute, N 2,200 revolutions per minute, FZ 0.14 millimeters, VF 1,200 millimeters per minute, AP 0.14 millimeters, and AE 25 millimeters. The aluminum coil coating process begins at the entry section, where the coil is unwound and joined to the previous one. The strip then passes through a cleaning section to remove contaminants such as oil and dust. Next, chemical pretreatment is applied to enhance adhesion and corrosion resistance. A primer coat is then uniformly applied, followed by a top coat in the desired color. Both layers are cured in high-temperature ovens to ensure durability and a smooth finish. Finally, the coated aluminum strip is recoiled in the exit section, ready for downstream manufacturing. At Fungus Blank, the investment casting process begins with the creation of highly precise wax models using modern injection molding machines. These wax components are assembled manually by experienced workers into a cluster called a wax tree. This step demands great care and dexterity to ensure dimensional accuracy and structural stability. Next, the wax tree is dipped into a ceramic slurry and then coated with fine sand. This process of dipping and stiffing and stuccoing is repeated multiple times in a fully automated and process-controlled system until a strong ceramic shell of the desired thickness is formed. The shell's thickness must be sufficient to withstand the thermal and mechanical stresses during metal casting. Once the ceramic shell is fully built and dried, the wax inside is melted out in a controlled furnace. This leaves a hollow mold cavity that exactly replicates the original wax patterns. The mold is then preheated, and molten metal, such as steel, stainless steel, superalloys, aluminum, or copper-based alloys is poured into the cavity. For demanding parts that require exceptional heat, acid, or corrosion resistance, vacuum casting is employed. After the metal cools and solidifies, the ceramic shell is carefully broken away, revealing the raw metal casting. Skilled workers remove the gating and runner systems and perform visual inspections. Depending on the part, only minor post-processing such as straightening or trimming is necessary. The result is a highly accurate near-net shape component. The parts may then proceed to advanced CNC machining, welding, and assembly stations, where they are transformed into ready-to-install modules or assemblies. Fungus Blank also offers just-in-time delivery and integrates seamlessly with customer logistics systems, ensuring high delivery reliability. Throughout the process, digital data exchange and simultaneous engineering between the client and Fungus Blank support rapid prototyping and efficient product development. In-house toolmaking allows precise and cost-effective production of injection molds. Residual ceramic material from shell building is recycled, contributing to the company's strong environmental management practices. Each batch undergoes rigorous metallurgical testing to confirm compliance with exact material specifications. Certified to ISO TS 16949, Fungus Blank places strong emphasis on planning and quality control at every stage to avoid downstream defects. Investment casting at Blank enables the production of complex, lightweight, high-strength parts with tight tolerances and minimal waste, ideal for applications in automotive, aerospace, medical, and precision tooling industries. The screw manufacturing process begins by loading a C45 steel bar into the Doosan Puma 300Y CNC lathe. The bar is securely clamped in the chuck to ensure stability during machining. The process starts with facing the end of the bar to create a clean and flat surface, followed by center drilling to guide further axial operations. The next step involves rough turning to remove excess material and create the general cylindrical profile of the screw. Using a turning tool, the machine then performs fine turning to reach the desired diameter and surface finish. After shaping the cylindrical portion, the machine switches to live tooling for milling the four-sided square section. The Y-axis movement and the spindle rotation are precisely synchronized to cut four flat surfaces accurately. Once the square section is completed, the machine prepares the threaded portion. A threading cycle is executed using a threading tool, which cuts the external thread with consistent pitch and depth. The tool path and cutting parameters are optimized by the CAM department to ensure long tool life and efficient cycle time. Finally, the finished screw is parted off from the bar using a cutoff tool. This integrated, automated process produces a high-precision screw with both square and threaded features in a single setup.